Hello guys, welcome back to my YouTube channel Anveshana Academy. This is Dr. Manjunath Channapgood. Dear students, in the previous class we discussed about sign convention for conduction heat transfer. Why it is minus sign. With some sample readings I tried to explain you what is negative sign in the conduction heat transfer. Dear students, come today I am going to solve some numericals on the conduction heat transfer. Okay, so numerical on conduction heat transfer. Dear students, I will read the problem first, then I will try to solve it. Okay, problem number 1. Consider a wall made up of brick with a thickness of 0.2 meters and thermal conductivity of 0.6 watt per meter Kelvin. The temperature on one side of the wall is 20 degrees Celsius and temperature on the other side is 30 degrees Celsius. Calculate the heat flux through the wall. So dear students, what actually he is telling now, he is telling that there is a brick wall and it is having thickness of 0.2 meters and one temperature at one side is 30 degrees Celsius and other side is 20 degrees Celsius, and that brick wall having some thermal conductivity, that is K, and it is having some thickness, that is T you can take or you can take dx, dear students, and it is having two temperature, one is high temperature, another one is low temperature. Hence what actually happening now, heat is getting transferred. Then he is asking to calculate how much amount of heat is going to transfer for unit area of the wall. He is going to ask, so that you can do here now. What all steps we need to follow, that we can see here, dear students. To calculate the heat flux, what all the steps I need to follow? First thing, what I have to do, I need to identify the wall parameters. What are the wall parameters he has given? Yes, he has given some wall parameters. What are those? He has given thickness of the wall, that is 0.2 meter, and that brick wall having some thermal conductivity, that is 0.6, dear students. Yes, I have to list out the wall parameters. Second one, that wall having two temperatures. So what I have to do, I have to list out the wall temperature. One higher side is 30 degrees Celsius and lower side is 20 degrees Celsius, dear students. Yes, wall temperatures also I have to list out. To do the calculations or to calculate the rate of heat transfer through this brick wall, I need to use an equation. That equation is nothing but what? Fourier's law of conduction, because conduction heat transfer is taking place in the brick wall. Hence I need to use the Fourier's law of conduction equation. With help of this Fourier's law of conduction, what I can do, I can calculate the total rate of heat transfer. I can calculate the rate of heat transfer per unit area. That is nothing but what? Heat flux, dear students. Then I need to interpret the results and I need to calculate the heat flux. This is the steps we need to follow to solve this particular numerical. Then come how to solve this numerical. Dear students, he has given there is a brick wall. So I will mark here, this is what? Brick wall he has given. There is a brick wall. Okay, this is isometric view and it is having some dimension, width it is having, height also it is having. Through that brick wall, what actually he is doing, he is transferring the heat. The amount of heat transfer we are going to represent with the notation, that is Q, and the thickness of that wall is dx. I will take it here dx. Some authors they will take small t, some authors they will take L, or some authors they will take capital L also. That's up to you, but I will take it here. The thickness of the wall is dx and heat transfer is Q, and that material, that brick wall having some thermal conductivity, that thermal conductivity I am going to represent here as a K. One thing, and that plate or you can call brick wall having an area, that area I will mark here as a capital A. Then heat is going to transfer from this space to this space. So what I will do, I will mark temperatures here. At beginning, at high temperature region I will take temperature as T1, then low temperature at lower side I will take temperature as T2. Hence heat is moving from high temperature region to low temperature region. That how I have shown. To solve this numerical, dear students, what I will do, this I will take it as my front view and I will try to draw the diagram. This is my schematic diagram. So this is what? So heat is moving from high temperature region to low temperature region through a brick wall. This is what? Brick wall. Brick wall I have taken, dear students. Fine. Then next, it is having a thermal conductivity. That thermal conductivity is K, and that having an area, that area I will mark here as a actually. So the heat is moving from this point to this point. So that heat is moving from this point to this point, right? The temperature at this point I will mark here as a T1. Temperature at this point I will mark here as a T2. So heat is moving from T1 to T2. When heat is moving through a brick wall, right, there is a resistance offered to the heat flow. That resistance I will show it here. That means what? T1, then resistance, then T2. That resistance I will mark here as a R. The value of R is equal to L by Ka, dear students. This is the given problem. This is the given problem. I have drawn the schematic diagram. Then I will list out the given data. What are the things he has given? Yes, he has given the thickness. So he has given the thickness. I will try to list out the given data now. I have drawn the diagram, right? So now, what is the thickness he has given? Thickness is equal to, he has given, that is 0.2 meter he has given, dear students. Okay. Then he has given some temperature. What is the temperature? T1. The high temperature region, that is T1, is equal to how much he has given? He has given 30 degree Celsius. Then he has given T2 is equal to 20 degree Celsius. Hence heat is moving from T1 to T2. 30 degree Celsius he has given. The next, what actually is given? He given thermal conductivity. What is the thermal conductivity? That you can see here now. Thermal conductivity, how much he has given? 0.6 watt per meter Kelvin he has given. Okay, so that I will list out, dear students, now. What is thermal conductivity? Thermal conductivity of material I will represent here K, that is equal to 0.6 watt per meter Kelvin he has given. That is what? K. Then what I have to do? I need to use the Fourier's law of equation. What is the Fourier's law of equation, dear students? We know already. We need to, because conduction heat transfer is taking place, I will apply Fourier's law of conduction. Fourier's law of conduction. What is equation for Fourier's law of conduction? That already we know. What is that? Q is equal to minus Ka into dt by dx. Okay, so now what I will do, I will take this A at this side. That means what? Q divided by A is equal to minus K into dt by dx, dear students. Okay, so now this Q by A we know already, where capital Q by A is equal to, that is small q. That means what? Rate of heat transfer per unit area is nothing but what? Heat flux. Then that heat flux is represented with notation small q. Small q is nothing but what? Rate of heat transfer per unit area, where capital Q represents what? Total rate of heat transfer in whole area. That you have to keep it in mind. Dear students, now what I will do here now, so therefore what I can do, small q is equal to K into, I will take high temperature region, that is what? Delta T is nothing but T1 minus T2 divided by dx. Okay, so what is the, I will try to substitute the value now. What is K? Yes, K is also given, that is 0.6. I will write it here. Then what is T1? T1 he has given 30 degrees Celsius. I will write it here 30. Then next minus T2 he has given, that is 20 divided by what is the dx? Dx also somewhere else he has given. Yes, that is 0.2 meter he has given. So then what I will do? I will try to do the simplification. How to do the simplification, dear students? You can see here now. So 0.6 into what I can do here now. So I will write it here now. 30 minus 20 is 10. I will write, okay, 30 minus 20. Then what I can write now? 0.2, dear students. How much you are going to get? You are going to get 30. So that 30 is nothing but what? 30 watt per meter square. 30 watt per meter square. That is nothing but what? Small q. So therefore final answer is the rate of heat transfer for unit area or heat flux is equal to, that is small q, that is equal to 30 watt per meter square. That means what? Dear students, if you are having minus sign, right, that minus sign indicates what? Decrease in temperature. Decrease in temperature. So you can mark here minus sign also. You can mark here, or else you can leave. That is understood that heat is going to transfer from high temperature region to low temperature region. Hence the temperature is going to decrease. The decrease in temperature we can represent with a sign that is negative sign, dear students. Okay, this is how to solve the numerical. Okay, dear students, one thing, how you got the unit here now. So dear students, you can see here now one thing. So here it is a K, right? I will write it here now. So what is K actually? That is thermal conductivity. Thermal conductivity has given in terms of what? 0.6 watt per meter Kelvin he has given. But I have taken temperature in degrees Celsius. Dear students, you can convert this into Kelvin, and this is also Kelvin. You are going to get this. That means what? 303 plus 293. Then minus, you are going to get same value. For that purpose, degrees Celsius, I put answer in terms of degrees Celsius. So what I can tell dear students, you can see here 330, you can convert it into Kelvin, and you can put 330 plus 273, that is T1. How much you are going to get? That is 303 Kelvin. So then T2 is equal to 20 plus 273, you are going to get 293 Kelvin. Then 303 minus 293 is 10, that is 10, you can take difference, that is 10. Then 30 minus 20, it is 10. For that purpose, what I have done, I have written it in terms of degrees Celsius, but you have to put answer in terms of Kelvin here, dear students. As I am getting difference same, I taken 30 minus 20, but you have to put it in terms of Kelvin. So therefore, how I can write the unit now? So K is what? Here, K is what? Watt per meter Kelvin, because I need to know how I got the unit watt per meter square. So 1 minute. Okay, so what is unit for K? That is watt per meter Kelvin into what is change in temperature? That is Kelvin divided by what? What is dx? Dx is the what? Thickness of the metal plate, that is what? M. So what I will do, dear students, here. So Kelvin will get cancelled, then meter is there, it will become meter square. Then here it is watt is left out, watt, I will write it here, watt, meter into meter, it becomes what? Meters square, watt per meter square. The unit for heat flux is watt per meter square. One thing, or else here, heat flux is nothing but what? I have written it here, Q by A. What is unit for Q? That is the rate of heat transfer, that is W. What is unit for area? That is what? Meter square. Hence, what I can say? Unit for heat flux is watt per meter square, dear student. This is how to solve the numerical. I hope you understood. If you really like my videos, please do like and subscribe and support me. Thank you.